Okay, what I would like to do is talk about, we're talking here about string alignment. Okay, we're talking here about the problem of approximate string matching. I give you a string, I give you a string S, I give you a string T, and I want you to find the minimum number of changes between our string S and our string T. Okay, the minimum number of deletions from one string, equivalently, or deletions from the other string. We could view these as deletions from this or deletions from that. We in general will assign a convention that these are deletions and those are insertions. Okay, so deletions and insertions are symmetric things, although they're with respect to, are you inserting it, a deletion into S is the same as a deletion from S is the same as an insertion into T. So we make the convention one is insertions, one is deletions. Okay? And you got to get that straight. But so long as you're consistent, it doesn't matter which way you do it. Okay? And a certain number of characters being the same. These are what we would call alignments. And a certain number of matchings of characters to things that are different. Q to R. Okay? So this might be A, Q, AAR. It might be match, match, match. Here we might have a delete. Here we might have a CC, something like that. Okay? And so a pairwise string alignment is finding the minimum number of changes, or the minimum cost sequence of changes, to be precise, to transform string S into string T. Okay? And since things are symmetrical, it's the same as the cost of transforming from T to S. Any questions about that? A good question is, what is this? And, if you don't have, okay, any questions? Okay? So what I talked about last class, and this is important especially for the non-CS people to get, okay? I'd like to show you an algorithm that we talked about last class that I wanted everybody to look at to decide they understood why it was correct. Here we have an algorithm for finding the smallest number of changes from string S to string T. Okay? And what it did is it worked at finding what is the minimum number of changes from the first I characters of S to the first J characters of S. So we had S, I, T, J. Okay? And the basic way it worked was recursive. Okay? It said that to compare two strings, the cost of comparing two strings, we're going to look at the right side of the string. There are three possible ways the match could end. It could end by the two strings having a alignment of those two characters, okay, be it a substitution or an exact match. If so, we would pay the price of that match plus the price of comparing the strings of the smaller subproblem. Namely, deleting the last character from S, deleting the last character from T, and then editing the other two strings together. Right? So the cost of ending on a match is the cost of the match plus the cost of aligning the prefixes of the strings. The cost of ending on a delete is the cost of deleting the character from one string. Here I have you deleting it from S. Right? Plus the cost of editing the remaining parts of the strings, which were, the string looked like this. If we chopped off this, actually it looks like in this case we dropped, well, this was called S and this was called T. Okay, we're deleting a character from S, right? We have the cost of that deletion, which is returned by this function indo, and the cost of aligning the rest of the strings, namely the string S minus the first character plus all of J. Okay? There are three possible options. If we can recursively compute the cost of the alignment on the smaller strings, okay, The optimal thing to do at the end is the cheaper of these three options, where we factor in each case, the cost of the last operation plus the cost of getting there. We find the min of these three operations, costs, that is the cheapest way to do it, and that is what we return. Any questions about the correctness of this algorithm? The correctness is an important point here now. Okay, I need people to understand why this is correct. Okay, any questions? Like, I don't understand why it's correct is a good question. Any questions? Okay, yes?
There can be more than one ways of transforming.
You're saying that it might be the case that out of these three ways, all of them might have equal costs, for example. In which case, we are returning a cheapest way of doing it. Not all the cheapest ways of doing it, right? If there are potentially lots of different ways, I'm trying to figure out, in this case, the cost. Here I'm right now, I'm not even returning the alignment. I'm returning the cost, right? So there may be many ways of realizing this cheapest cost, right? I'm just telling you what the cheapest cost is, okay? In general, when I print out what is an alignment here, I'm going to print out an alignment realizing the cheapest cost. And I'll say that they're all equivalent. When you use your GPS device in your car, what do you want it to do to tell you you're driving between here and Brooklyn? What is it you want to know? Do you want it to tell you that it will take you 57 minutes to Brooklyn and here's a way to go? Or do you want to be told that there's 7,363 ways to get to Brooklyn in this amount of time? Okay? And here they all are, listed one after another. Okay? It's a similar problem that we're looking at here. Any questions? Yes?
Deletion are the operators. One is assigned to B1 and another to in the top.
Well, okay. So in my code here, I'm showing you real code. What's interesting here, you're saying why is one costing different than the other? This is not a cost. This is a symbol. This is an index. This is because I am trying to write my code so that I could put it on a slide. Latched onto the kind of clever idea, I hope, instead of giving three outputs here and finding the min of three separate variables, I was basically storing it in an array of three elements and finding the min of that, right? So these are just indices saying that matches. This is really saying that I'm storing the first thing in the 0th element of an array, the next one in the first element in the array, the next one in the second element of the array. Okay? Any questions? Okay? Any questions about this code and why it is correct? Okay? Yes?
Should this opt be local, not global?
This opt is telling me the optimal cost of any way of doing it ending on a match. That is a way to think what the opt is doing. There are three possible ways to end my matching, my alignment, right? I could end on a match or a substitution. I could end on an insertion, or by changing this to be an S and this to be a T, I could end on a deletion, right? There are three possible cases. This is recursively finding the optimal cost of ending on a match. This is finding the optimal cost of ending on an insert. This is finding the optimal cost of ending on a delete. And I claim the minimum cost alignment is going to end on either a match, an insert, or a delete. Why must it end on a match or an insert or a delete? Because there's no other option, right? It's got to end on something. There's only three ways it can end. I am finding the cheapest way to end in all possibilities. Okay? And then I am going to take the best of those three. That is what I am doing. That is why this algorithm is correct. Okay? Any questions? Kind of like the same way of finding the best way to drive to Brooklyn. If we're driving from Stony Brook to a particular block in Brooklyn, there were three roads at that corner, right? There was an optimal way. What is the optimal way of getting to Brooklyn? It is either I got through and went through this road, in which case the cost of getting to my spot was the cost of driving to here plus that last leg, right? Or it was the optimal way to get to here plus the cost of that last leg, right? Or it was the optimal way of getting from there to here and getting to that last leg, right? The cheaper of these three is the cheapest way to go, and that is exactly what I'm doing here. Any questions about the correctness? Okay? Yes.
Let us say two characters do not match, S of I and T of J.
Right?
Then is it reasonable to assume that match of Si and Tj will return some infinitely high number?
The match is going to be the cost of turning, if you wish, this character into that character, right? If the cost of a substitution is always 1, then the cost of turning an x into a y is 1, right? That's a conventional thing, right? You might imagine a different thing. This match is an abstraction, okay? It's a function that will return an int number, presumably between 0 and 1, okay, of how much it costs to turn an S sub I into a T sub J. In the case the character is the same, it should be 0. Depending upon whether I want to return partial credit, if the letters look similar, I might give something less. But this is application specific, right? It tells me what's the cost of that character thing. Okay, and if they're a match, I get away for free. If they're different, I pay a price. It may still be the optimal alignment, requires paying the price. Okay? Any questions? Yes.
My question was, what if we declare this opt variable as a global, not local, then is there any problem?
No, this is a local problem. This is local. See, local. And the reason is, I am right now, the way I am solving this problem, this is the important thing to see here. I am trying to figure out, in editing these two, I am trying to figure out what am I going to locally do at the end. To figure out the best possible move at the end, I need to know the cost of getting to this place. Again, let's think back to the Brooklyn, the road example. This actually may be a good example here, right? There are 3 roads leading to the corner. There's a block here. There's a corner I want to get to in Brooklyn, right? There are 1 block. It's the intersection of 3 streets, right? Which is the best street for me to go down it? The shortest path from Stony Brook. I can't decide this issue locally, right? You can't look at that block and say, which is the best way to come from Stony Brook? Just looking at that block, right? The decision of which one you make depends upon the length of the blocks, right? But more importantly, the cost of getting to each one. That is how, once we know the cost of getting here, and the cost of getting here, and the cost of getting here, then looking at the differences in the blocks. The total cost here is the cost of getting to here plus that last leg. Once we know that, we can decide which was the right last leg to take. Okay? And that's exactly what we're doing here. We're figuring the optimal cost of ending on each of the 3 possible last legs. Match, insert, or delete. Right? The way we do that is find the cheapest cost up to that point by calling it recursively. See, recursive call. Plus the cost of that last step. And to ask you a question about whether opt should be global or not. Because this is a recursive procedure, opt has to be local. Okay? Because when you solve this thing, when you run it, the first thing it's going to do is recursively call the function itself. It's solving a smaller problem. And there's going to be a local opt to do that. And to solve that, it's going to be a smaller problem. And it needs a local opt to do that. Bop, bop, bop. Until it gets to the basis case, where one of the strings is empty. In which case, it's very easy to figure out the cost of changing the string to it. Right? How much steps does it cost to turn Skiena into an empty string? Well, you've got to delete the S, the K, the I, the E, and the N, and the A, right? So that's that problem we don't need. We can solve that basis case easily. Okay? Any questions about this? Okay? It's important to understand why the recursion is correct. Okay? And for some of you who don't know too much, haven't had too much programming experience, recursion is a tricky thing. The idea that the function is calling itself seems weird. Okay? If you find that weird, Google something about recursion in Wikipedia or in an algorithms book, and then come by and talk to me or the TA if that bothers you. Any questions? Yes?
It was good to refer to this as an exhaustive search, right?
Well, this is a recursive search. This recursive algorithm. This is an exhaustive search is exactly right. Okay? It's trying all possibilities. And when you look at the running time of this thing, ka-chunk, let's try killing this. Ka-chunk. Let's try previous. Boom, next. And when you try to run this thing, it pays the cost of a recursive search. Okay? If you ran that program, it will find the optimal alignment between two strings, but it will be ungodly expensive. And when I ran it, I remember I could solve strings of length 12, and then longer than 12, I didn't want to wait. Why is that? What's it doing? It's saying, I want to edit two strings, one of which is of length 12, and another one is of length 12. In order to do that, I've got to make 3 recursive calls, basically. Right? One to the case where it was 11:11 when I hacked off from both. One was the cost 12:11. One was the cost 11:12. When I recursively do these ones, like this one over here, I'm quickly going to find 11:11 again. And so this whole subtree of computation is going to get repeated recursively when I do this thing here. Okay? As a recursive call, I am doing a lot of repeated work. In fact, I claim the program is only going to be called on a small number of different arguments. And by storing that up, I can make this much faster. What is the example? Go back to the program. If we look at this program, again, I now have shrunk it, but if we look at this thing, S and T, the character strings never change. The only thing that's changing are the indices in the string. Everybody see that? When I make a recursive call, I'm always passing S and T unchanged. The only thing that's changing are the arguments. And they go always, the lowest they get is 0, the biggest one they get is I. The other one is the lowest it gets is 0, the biggest one it gets is J. If we assume that we're calling them on the length of the strings, the total number of possible values of string compare is basically the product of I times J. If both strings are of length n, that would mean it's quadratic. Okay? Any questions about that? And so our idea is going to be to speed this up by saving those partial results. That is the big win here. Okay? This is the big idea of dynamic programming. Dynamic programming is a great algorithm idea. Okay? What we note is that we had a recursive algorithm. We were doing exhaustive search. But we were doing it in a dumb way because we were repeating steps in our exhaustive search again and again and again and again. Okay? We noticed that the number of recursive calls, they were only the length of S times the length of T, distinct different calls. Store the answers to these calls once we have them. We never need to compute them twice. And now instead of it being exponential, something like 3 to the n, which is, actually it would have been something like 3 to the n, 3 to the n, between 3 to the n and 3 to the 2n, if you did the brute force search. Instead, we're going to note that this is going to be quadratic because there's only a small number of different calls. Any questions about that? So what we're going to do is, for dynamic programming, is store the answers up in a table instead of recomputing. And as we'll see, that's going to turn this exponential algorithm quadratic. Any questions? The take-home lesson from this is that dynamic programming is a very useful thing. Okay? It is a way of computing recurrence relations, recursive programs, by storing partial results. And once you get good at algorithm design, you can smell when a problem is dynamic programming. Okay? It's a very easy thing. When you do it is when you have a recursive, or when you can define a recurrence relation on something, and when the structures are ordered from left to right. So character strings. A character string is ordered from left to right. A rooted tree drawn in the plane is ordered from left to right. The leaves get ordered left to right. So there are lots of different problems. Whenever you have a structure that has kind of an inherent left-right order to it, dynamic programming is one of the things you should be thinking about. Okay, we'll be thinking about it here in strings, but that's the key distinction. Any questions? Okay. Let's talk now about how we use, let's look at the dynamic programming example. So to implement our edit distance program with dynamic programming, we said we were going to use a table to store the results. Our table is going to be a matrix that is going to be basically for all values m sub ij is going to tell us about the cost of editing a string. If we have a string s and a string t, m sub ij is going to describe a pair of indices, and it's going to describe the cost of editing the prefix of length I on S to a prefix of length J. So we need to define at most if the string is of length maxlen. Okay, there's a maxlen by maxlen table. Each cell of the table, the main thing it's going to keep track of is the cost. That's really what we need if we want to compute the cost. We will find that it is also useful to store the parent. The parent is really the decision that we made to reach that point. If you think back to our recursive program here, ka-chunk, 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 there was a decision that we made, right? We had to decide, did we want to end on a match or an insert or a delete, right? One of those three is going to be the best ones. Once we have figured out which is the best one, it's probably good to store also what that parent is. Okay, and that we'll see is going to be useful in reconstructing the alignment. Any questions? Any questions about where we are so far? That said, let's look at the dynamic programming solution of edit distance. Zoom, zoom. Okay? Here is the string programming the string algorithm version that takes quadratic time instead of exponential time. Okay? Like the other one, okay, unlike the other one, it is not recursive. String compare is here. There is nothing in here that calls string compare. Instead, we have a dynamic programming table, which I think I declared globally before. I used those declarations before. And now what I'm going to do is, just like before, I am going to find what is the optimal way of ending for a particular I and j. What is the optimal way of ending in a match, in an insert, in a delete? Okay? And I am going to go through those three possibilities and pick the minimum. Okay? So this is exactly like I was doing in the previous one. The only difference of note, really, there's two differences of note. The first is that instead of using a recursive call, I am looking up the answer from a table. Does everybody see that? Before I had a recursive call, Here I'm looking up in my matrix M what the story is. The other difference is that I am specifying an order of evaluation. Before, when you evaluate it recursively, you're basically starting out from the ends of the string. When we fill in the dynamic programming table, what we would like to do is to start from the cases that are easy and keep working from the easy cases out. Okay? That's the other significant difference here. Any questions? So when editing a string S into a string T, there are, N characters, M characters. What cases are easy? The first easy case is the cost of, what does it cost to compare the first I characters of S to an empty string? And this, I claim, is something that we can determine. It's a function of the length of the string, right? To convert Skiena into an empty string, you had to delete each character of Skiena. We can fill in the initial row and the initial column based on our problem knowledge. In general, we're now going to solve for a particular ij value. If we want to compute the value of cell ij, there are 3 cells we're going to look at. Maybe I'll write this here. 3 cells we're going to look at. To fill in ij, if we look at a deletion, that's I minus 1j. If we look at an insertion, that's ij minus 1. If we look at a match, we're changing both indices. That's I minus 1, j minus 1. These are the 3 sets of indices that we're looking at. And if you think about it as a table, we are marching through this table in either a row-oriented manner or a column-oriented manner. It doesn't really matter. All that matters is that we arrange our loops, I and j, so that when we look for a particular value, we want to compute this value, the 3 previous values that we depend on have been computed. Any questions about that? Okay. Any questions about that? We'll see an example in the near future, in a few minutes. Okay? But does everybody get the basic ideas of what this is like? This is recursion, except that instead of recursion, we're doing table lookups. And because we're doing table lookups, we better have what we want before we look it up. Okay? And that's why we're forced to start from the beginning instead of the end. Any questions? Yes?
So row init and column init just fill in the first row and first column of the matrix?
Yes. So what I've done here cleverly, okay, is I have built a very, very general string comparison, okay, that will let us solve lots of problems. You can specialize it by what are the cost of your row and column inits. You can specialize it by what are the cost of your to delete a character, to characters or substitution costs. And there is one final customization that you can do, which is where is the end cell that ultimately has your answer in the matrix. So goal cell is another routine I wrote. In the case of editing S to T, ultimately the answer we care about is what is the cost of editing all of S into all of T. Okay? But these are, I'll go through what these functions are, but these are how I'm parameterizing my thing, so that the same general dynamic program will solve many, many, many problems. Questions about that? Okay, yes?
Wouldn't you need an extra row and column to M in addition to S and T, since you're considering not using a character from T or not using a character from S? From the init?
Well, the init is, if you want to think about it, the init should be sort of comparing the empty string, okay, the empty prefix. So I think of the init as it should be in position 0, Okay? We haven't looked at what, let's look at what this function is. I mean, in principle, the init is the cost of editing the empty string into a prefix of the other string, right?
That's what I'm saying. So if you were comparing S to an empty string, then you're going to need an extra. If T is doing the columns, then
So you're saying I need n plus 1 columns
Yes.
for a string of less than n, and I agree with that. Okay? Any questions? Yes.
The point is, must be on the bottom right corner, exact position.
Yeah, so my basic vision is this is going to be, in my vision of how I think about this, this is the 0, 0 point, the empty string going to the empty string. The ultimate cost is how much does it cost to take the first n characters of S and edit it into the first m characters of T. That is going to be this cell. Okay? Any questions? Okay? For this problem, that's clearly the right goal cell, although for some of the other ones to look at, it won't be. Any questions? Yes?
So because of what I said, you have to really do a little bit of adjustments there with
Your indices.
Yes.
Okay, so the indices, you have to get the indices right.
Because the string, you don't necessarily want I just to go from...
The way that I did this, again, you can look at my, I have posted some code, which is possibly something I wrote, okay, of how I would did this, okay? Or you can look in one of my algorithms book for how I did this. I think what I did to make the indices work out on this is I took the string and I put the first character as a blank. I padded the real string with a blank character so that it did its right thing and I then ignored, okay? But you've got to get the indices right.
Right.
That requires precision, but that's not the big picture here. Any questions? Okay. Any other questions about this procedure? Okay. So what can we say now? Boom. That's inverse, reverse, next. Okay. The key point here is that the reason it works is that we're filling in a matrix. Okay, we'll assume that we have the defining cases of this row and column. We're going to fill these things in so long as the leftmost, the upper, bottom, and leftmost cells exist. One way we could do that is by marching along each row, and we're guaranteed it always exists. Another way we could do it is by marching down each column, right? And it always exists. We could even, if we want to get creative, fill it in like whatever order you want, right? So long as the three guys are there. But it's harder to program it to be creative, and there's no reason to, right? So long as we march down rows or columns, that will work. Any questions? That's the evaluation order issue. Any questions? Okay, so let's look at now, what's the next one? So I told you I've parameterized it. I have given you an extremely generic edit distance thing. First thing I had to do was to specify what I will say the cost of a match or a delete. Here's my match function. Again, you may not read it too well from there. But basically what this says is that if the two characters I give you are the same, I'm returning 0. Otherwise, I'm returning 1. Okay? So this is counting the number of characters. Every substitution is 1. Right? You want to change it? Change it. It's generic, right? I have said that the cost of deleting a character, okay, is always 1. Okay? That's how this is implemented. What if you say, oh, gee, I really hate deleting Q's. Q's are my favorite letter, and I hate deleting Q's. Okay? I want to charge you 3 for that, so you don't delete Q's. Okay, fine. Okay? You can implement that, changing the character deletion value, right? I also gave you problem-specific insertion and column initialization and row initialization procedures. Basically, what did I do? When I, When I filled in a row, this was the cost of editing the first I characters into an empty string. Basically what I said was the cost was going to be equal to I. Okay? Here I'm saying that I insertions costs I times the cost of one insertion, which was 1, right? If you want to charge something different, you can. That's the initialization costs, right? And what I did was I initialized the, basically not only the costs, in general, either my row or column, I initialized it the cost to I for deleting or inserting I characters. My main difference was in the parent operation. Okay? I told myself that if you were inserting things on a row init, the operation that you were doing was basically called an insert. On a column init, it was called a delete. That's because what is considered to be an insertion in one string is a deletion from the other string. Right? So what parent kept track of is what is the operation that you were last doing. So if I was editing S to the empty string, okay, my last operation was, depending upon how I want to think of it, it could either have been an insertion into T or a deletion from S, right? Once I established a convention, you know, it's going to be one or the other. The last operation is going to be the insert or delete. Any questions? And I did the special thing that if I had a 0, the special case of the empty string into the empty string, the previous operation was nothing. And that's why I have a special -1 there. Any questions about my generic row, insert, delete, and initialization functions? Any questions? I also have, I said, one other function, which was my goal cell function, which returns the final cell of interest. Here, the goal cell is always going to be the one that is at the, if I am editing a string of length n into a string of length m, the goal cell is always the cost of editing the full string into the full string. So it is always going to be the length of the string, first string, and the length of the second string, with the appropriate ±1 adjustments to make the indices work out right. Does everybody agree with that? Okay. Does everybody see why it's something like the length of the string S by the length of the string Y, S by the length of the string T? The ±1s I don't care about. That depends how you code it up. Okay? You care about it because if you don't get it right, your program's wrong. But we agree that that's a detail, not a big picture thing. Any questions? Okay. So that is my full program. And what's interesting, as I will show you later, is you can do all kinds of special things by changing these insert, delete, goal cell things to make the program do other interesting dynamic programming things. And we'll show that a little later. Any questions? Yes?
And this is considered dynamic programming because it stores the information?
Dynamic programming, as I define it, is computing a recursive function by storing partial results. So it's the table that makes it dynamic programming. That, I guess, is what makes it dynamic programming. Okay? Any questions? Yes?
So to reach this smallest edit distance, the path is not unique, right?
Path is not necessarily unique any more than the path. And forget about Brooklyn. Let's think about Manhattan. Okay? Manhattan, everything's on a grid, right? If I want to get between Penn Station and, there's an Ethiopian restaurant I'm going to Saturday night. Okay? It's a certain number of, it's something like about 10 blocks down, in fact, and it is about 3 avenues over. Okay? What is the fastest way to walk to this restaurant? Well, because it's on a grid, this is a fastest way. This is an equally fast way. Does everybody see that?
Depending on traffic lights.
Well, I'm walking. There's no traffic lights. No issue here. There's many equally fast ways of doing it. I am finding that the cost of minimum amount of time, and I'm giving you one path that does it. Okay? Because if I gave you all of them, there's an exponential number of them. You don't want to see all of them. You want to see one. Okay? Any questions? Okay? Any questions about that?
I guess you could also tally up how many of those there are, not even just...
Using dynamic, can you count how many fast there are? Suppose you don't want to know the fastest way of going there. You just want to know how many ways there are of doing it. You can do that with dynamic programming.
No,
but that's
what I'm saying is how many fastest ways?
How many fastest ways there are. That you could also do by dynamic programming if you really want to know. Okay? So if your GPS wants to come up and tell you there's 96 fastest ways to get there. Okay? Algorithmically, it's not that much different, actually. Okay? You could use dynamic programming for that. But as far as I know, not too many people want their GPS to tell them that. Okay? Any questions? It's an interesting question. Maybe people do. Okay? Maybe that's something that would keep, in the competitive GPS industry. Any questions? Okay. So here is an example. So if you're confused about what's going on, look at this example and make sure you understand this. Here I am going to look at editing two strings. The cost of turning thou shalt not into you should not. Maybe I'm updating the Bible or something like this. Okay? What is the number of changes to go from thou shalt not to you should not? Okay? Let's zoom in. Zoom. Okay, sorry. Boom. Zoom. Zoom. Okay? So what is this table showing me? Okay? First thing to note is that I am editing this string into that string. Right? Does everybody see that? The first thing is, you notice I had that padded with blanks. That's supposed to denote the empty string, right? What is the cost of turning thou shalt not into the empty string? Well, you've got to delete T-H-O-U space S-A, right? For every character, to delete one character, cost 1. 2 characters cost 2. 3, 4, 5, 6, 7, 8. Does everybody see why this column has the values it does? This is the cost of how many deletions it takes to delete the first I characters of the string S, okay, into the empty string, if T was the empty string. Any questions? And a similar phenomena is along this way. This here is showing me how much does it take to turn the empty string into you should not. Well, I've got to add the Y-O-U space S-H-O-U-L-D space N-O-T, right? So I have to add 1, 2, 3, 4, 5, 6, 7, 8, 9 characters as it gets longer. Does everybody see that? So these are my initialization conditions. Does everybody see that? Boom. Boom. Okay? Now, what am I going to do? What is the cost? How can I go and turn, in this case of this cell, there's a first interesting open cell. What's the cost of editing a T into a Y? I claim there are 3 ways I might think of doing it. One possibility is I take the empty string and the empty string and then substitute the Y for a T, right? That would be 0 plus 1 or 1, right? The other way I could have done it was I might have taken the empty string, added a T to one, and then added a Y to the other, right? That would be 1 plus this, or 2, or 1 plus this, or 2. What was the minimum of the 3 possibilities? The min of 1 and 2 and 2? It was 1. Does everybody see that? That's why this got chosen. Why is this element 2? What is the cost of editing TH into a Y? Well, I claim I've got 3 possibilities. I could take the cost of editing a T into an empty string and then pay the cost of the substitution. That's 1 plus 1, right? Or I could have taken the cost of editing a T into a Y and then pay the cost of adding the h. That would also be 1 plus 1. Does everybody see that? Or I could take the cost of editing th to a blank and then add a y to the other string. That would be 3. Okay? Government contracting, maybe you'd pick the last one, right? But if you want the minimum cost way, there's 2 minimum cost ways, right? Which of these is better, going diagonally or going down? Down? It doesn't make any difference. There are 2 equivalent ways of getting there.
I like down.
You like down? You pick one of them, okay? If you like down, you can pick down, okay? But either one of them will get you to here at a cost of 2. Is that right? In general, you can pick any spot in this matrix and see why it is being done. Let's pick our picture. Boom. Where do you want me to look at it? Here's a nice spot. Right? Why is this? What is the cost of editing? Thou blank s into you sh. Okay? What is the possibility? Well, I could come from here and say that I have gotten 3 to get to this point, and then I want to convert an s into an h. That would cost 1, right? So it would cost 4 to come down this way, right? I could go from here, it would take 5, and then pay the insertion. It would cost 5 to get to that way, right? Or I could come from here where it costs 2 and delete the extra character, right? Which is the better of those possibilities? They're coming from this way. Does everybody see that? Okay? So why is this an n squared algorithm? Or n times m algorithm? If this is n, this is m. I've got n times m cells. At each cell, I am going to look at a constant number of things. I'm going to do a constant number of character comparisons. And I'm going to pick which of these 3 numbers is smallest. It is a constant-sized problem. I am going to solve n times m times. Any questions about that? Okay. Any questions? Okay. Let's look at this thing and see what ultimately happens. Any other questions about the example? What is the cost of editing thou shalt not into you should not? The final cost, I tell you, is going to be 5, right? What is the path that got me to this place? That will describe the alignment between the 2 strings, right? The right way to do this would be to look at the parent of each cell, okay? I think the reconstruction, and there's no reason why you should believe me on this. Well, it's not, you say keep going towards the minimum number. That's not necessarily possible, okay? Because it may be that the minimum number here, the cost here is considered to be 4, right? It could be that this character is not the same as that character. So it might be I'm not able to go backwards, right? Okay? But there is going to be some kind of a path. And I'm just going to make this thing up now. Although here you notice there's 2 different choices, right? There is going to be a path, okay, that is going to describe how you move around this thing, okay? And that path, when you reconstruct it, each step on this path is going to be an insertion, a deletion, or a substitution, okay? The claim is that the cost is going to be 5 for doing this. Any questions? Okay? How do you figure out what that path really was? Boom. Go to my next page. I give you the parent matrix. Okay? So what were the parent matrix values? Remember in here we had those things defined? What were they? Does anyone remember? One was, I believe, the match. 2 was presumably, what was it, an insert or a sub? What? What? 0 was a match. I probably added 1 to it to make it non-zero, okay? What was 2 and 3? One was an insert? What? Insert, and 3 was delete?
Well, it depends on the reference.
Okay? What this is telling me is the parent of this cell was up here, right? The parent of this cell was up here. The parent of this cell was up here. The parent of this cell was up here. Here I'm cruising quite a bit. The parent of this cell was over here. Oops. Now this is no longer, okay, if I'm looking at this thing, the parent of this cell now is 2. That, I think, meant that I came from here. Okay? The parent of the cell was a 1, 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 was a 3, which meant it came from up there. Right? This was the alignment that our string, that our thing went through. Does everybody get that idea? We stored the decision we made at every point. By walking backwards through this matrix, we can reconstruct what that sequence of moves was. Got us there. Any questions about that? Okay, yes?
How do you read this? How do you go back from the end to the...
How did I read that thing back? Because I knew that this was a code. Remember, I stored the parent. The parent was either, in my last move. The parent meant what was my last move, right? What is it that got me to this cell? Either it was a substitution / match, in which case I came diagonally, or it was an insert, in which case it came from that way, or it was a delete, in which case it came from that way, right? So recognizing, how do I interpret it? I interpret it using this coding table, right, of what 1, 2, and 3 mean, right? And from each cell, it tells me how to get back to my parent, right? And I know I will eventually walk back until I got the -1. That was my initialization, remember? Meaning that I now would fall off the grid with my next one. Any questions about that? So by storing the decisions I made, I can now reconstruct what was the alignment that it took, the path it took to convert you shall not, should not into thou shalt not into you should not. Any questions about that? Okay. Any questions about this example? It's important to understand the example. So if you're saying, oh, I'm confused, recursion, complicated, okay, go and look at the example and fill in the table by hand. Maybe it's a good question to have you guys fill in one of these on the exam. I haven't thought about that, but that's a good one. Okay? Maybe someone tell me that. Any questions? Okay? But it's important to understand this strategy under this kind of level.
Why all 3s are below the diagonal and all 2s are?
Why are all 3s? That's an excellent question. You notice something interesting. Why are the 3s down here and the 2s up there? Okay? The answer is you're editing thou into you should not. Okay? I know you're darn well going to have to do a lot of deletions from you should not in order to get to thou. Does everybody agree with that? And here, you're going from you into thou shalt not, right? And because, again, so here, we're now going to, here, the corresponding notion of what was a deletion is an insertion into this, right? We're transforming this into this. To transform the short thing into a big thing, we were deleting from the big thing, okay? To transform the big thing into a short thing, we're inserting into the big thing, into the little thing. Does everybody see that? That's why these are 3s and those are 2s. Okay? Good question. Any questions here? Any questions about how this is working? Important to go through the example and make sure you understand it. Okay? Any questions? Boom. Okay? Any questions about the example? Okay, let's say next, and let's try zoom. Okay, so what I will tell you is, if you understood my example, okay, what's interesting is, once you have this dynamic programming matrix, okay, you can walk backwards through it to reconstruct the alignment. That's what I just did, right? You follow the pointers and you walk from the back to the front to figure out what the right solution is, okay? And that shouldn't be that hard. The only thing that's a little dissatisfying about walking from the back to the front is that your answer comes out backwards. Does everybody see that? You want to edit string S into string T, and I'm telling you what the things you did from this end, okay? Whereas the natural way to read it is, what are you doing from this end, okay? So you can either do that walk from the back of the matrix up and then reverse it, okay? Or you can use a little slick recursive algorithm here, okay? Zoom, to do the reversing for you, okay? And this may be a good example. Figuring out why this works is a good example of how recursion works. For my non-CS people, hopefully the CS people know this, okay? What am I doing? To reconstruct the path from my end state, what am I going to do? I check to find out what my parent was. Either if it was the -1, that meant I fell off the grid, right? So I end this. I have reached the beginning of my grid. Or my parent was either a match, an insert, or a delete. That tells me the direction of my previous goal cell. If it was a match, and I'm ij, my parent was at I-1, j-1. If it was an insert, my parent was at I, j-1. A delete, I-1, j. What I'm going to say is recursively reconstruct the path, okay? And then, once I have that, then output the corresponding operation, okay? So this is saying basically, figure out what the path was to this cell, print out that path, and then output whatever you want to denote that at position ij we ended on a match, okay? This is a generic reconstruct path routine. You may want to do something different with your path. What I wanted to do was just to print it. And so my generic path thing were simply functions that said, what do I do on outputting an insert? I said print out an I. On delete, print out a D. On matching, either print out an M or a substitute, depending upon whether or not the characters matched, right? When I took a diagonal step to my parent, it could have been because I had a match, the characters were the same, or it could have been I decided to pay the cost of a substitution. Any questions? Once you do that, you get an edit sequence, okay? And the claim is, this tells us how to convert thou shalt not into you should not. How do you do it? Well, first start out with a delete. Delete that. Then do a substitution. The H is going to go and become a Y, right? Then do a match. Match. How many matches in a row? 5. Match, match, match. Then what am I going to do? Do an insertion. What am I going to do here? It looks like I'm going to insert an O. Okay? Once I did the insert an O, what am I then going to do? I'm going to do a substitution. The substitution is that the A is going to go to the U, right? Then match the L's, and then do another substitution. The T will go to a D, right? And then match, 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 match. right? And thou shalt not became you should not. Any questions about that? Okay? Do people see how we call this thing an alignment? Okay, this is the description, basically, of what characters in here were assigned to what characters in there. Okay? This describes how you do the transformation, and what is associate corresponds to what. Any questions about that? Okay? This is what we seek to find in doing a string editing thing here. Yes?
So apart from the actual distance, how is this useful and this sequence, the reconstructed part?
Okay, so how is it that this is useful? Okay, to actually show me what the alignment is. Well, it depends what you're trying to do. So one argument would be that, let's say somebody comes back to you and you say, getting back to the GPS model, okay? You know, if somebody says it's going to take me 57 minutes to get to Brooklyn, my first question could be, prove it, meaning tell me how you did it, right? Now you tell me there's 5 changes between thou shalt not and you should not. The next answer is prove it, right? This alignment is the proof. It's actually the description of how you do it. Now the question is, why do you care about that alignment? And it depends upon what your application for why you were doing the string matching was. Okay? One reason for doing the string matching in a biological sequence, very well, might be here you have gene 1, here you have a gene 2, right? There were evolution. This is your gene in your chicken. This is your gene in your turkey, right? And there have been changes in going between a chicken and a turkey, right? This is telling you what is the difference between a chicken and a turkey. You might say, oh, the distance is 7, okay? But when I say what makes a turkey, you have to actually describe what those changes are. And this shows you what those changes are, okay? So that's an example of why you care about the alignment. In general, a biologist in sequence alignment is not interested in the cost. They are interested in what happened. Why did this A turn to a C? Oh, that's why. Okay? And now they understand what happened. Okay? Any questions? Okay? Any questions about how this editing thing works? Okay? It is important to understand things to this level. Okay, we're going to build on this, and at some points it'll get maybe a little hairy, but it is important to understand it at this level. If you didn't get it, study this. The book has a good, I think, introductory version of this. So if you read the textbook, you don't get this. It's important to understand the dynamic programming. There's a copy of the textbook on reserve in the library, I believe, and yes, there is. We put it a special one on reserve. Okay, check there. And this may help you. There's also a copy of my algorithms book. So if you really want to read how I would do it, there's a copy of the book algorithms book I wrote on reserve in the library also. You can check that out. Any questions? Okay, yes.
When you backtrack in the matrix, when you backtrack, you always went into like the minimum, right? And that's how you got the path.
So the question is, how did I backtrack in the matrix? The real way I backtracked in the matrix was by following the parents, okay? This is the right way to backtrack, okay? This is what's telling me what to do, right? Right. Now, when I looked at the cost matrix, okay, before, I sort of made some guesses as to which way I went, because in general, I'm going to follow the cheapest path, right? But whether it's possible or not depends upon the characters. In fact, if you look at this carefully enough, you'll see you could reconstruct what the parents were, okay, from the costs and the character sequences. But either if you see that, you're right, okay? If you don't see that, don't worry about it. See everything else I've said here. Any questions? Okay, any questions about these routines before I move on a little bit? Okay, good. So let's move on. Boom. Boom, 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 boom. I've talked to you about these cost functions. I know I define my edit distance in terms of generic cost things. That's because by choosing different values of those various initialization and cost and other functions, you can compute different things, okay, using the same basic dynamic programming code. So let's look at what would happen if I made the cost of substitution very, very high. Okay? So right now, before I had cost a substitution to be cost 1, an insertion to be cost 1, and a deletion to cost 1. What if I jacked up the cost of a substitution high enough? Yeah?
You wouldn't see it.
I wouldn't do it, right? Does everybody agree with that? I jacked up the cost of a can of Coke to $365. No one would buy a can of Coke. Is that clear? Okay. How high do I have to make substitution go before it's completely undesirable? Okay. Let's think. What? You say n plus 1, you say 3. I say anything greater than the cost of an insertion and a deletion.
Right.
Does everybody see that? How can I transform character A into character B? Well, one way I could do it is delete the A and then do an insertion of B. Does everybody agree with that? So long as that cost is greater than 2, it's undesirable. So long as it's 2, it's unnecessary, right? So what happens, though, if I make the cost of a substitution so high? What is the desirable alignment between two strings? Let's look at an example here. Suppose I want to now convert, I don't know, I'm going to make something up. A, B, B, B to B, A, B, B, B. Okay? If I make a substitution very expensive, for substitutions are more obvious, I guess, if the character is completely different. Okay, so there's a C here, right? What would be the right alignment of this if the strings are, if I want make the cost of a substitution very, very high? I claim all I'm going to want to do are insertions and deletions. Does everybody agree with that? What is the cheapest way to convert, in this case, ACBBA into BABBB when I'm not allowed any kind of substitution? It's pretty clear this new character, this character that didn't appear in the other string, is toast. I'm never going to want to do anything but delete it, right? What is the right alignment between these two strings? Okay? I claim it's probably going to be something like B, or A minimum cost 1 would be something like this. Does everybody see that? I claim I could get 3 exact matches plus 1 delete, 2 delete, 3 delete, 4 delete. Does everybody see that? Okay, am I right about the number of deletes? Yeah. I've got 3 matches in each string. That meant that there were 2 leftover things. Does everybody see that? I might come up with a different answer, okay, if I was allowed substitutions. In fact, let's look at an example where I'd come up with something different. If I want to turn car into coulter, any Lisp programmers we have here, okay? If I wanted to do this and I was allowed costs for everything, it would be 1 substitution. Does everybody agree with that? If I'm not allowed it, it's going to be the cost of match, match, delete, delete, right? Or insert, delete, okay? What I claim is if you make the cost of substitution so high then I claim that the optimal alignment, the only goal is going to be to maximize the number of characters that are matched between them. Okay? The only way to save money is to match characters. And I claim that the optimal alignment under this is going to be the alignment with the maximum number of these matches, or the longest subsequence that is common to the two strings. Okay? So if you want to figure out what is the longest subsequence common to two strings, it is exactly equal to the edit distance with the appropriate cost function. Okay? Any questions about that? Okay? How many people see why this is the right cost function to compute the longest common subsequence? Okay? Good. Any questions about that? And there are a bunch of other problems that you can solve with the right cost functions. The most important one of which is, again, I do that there. The most important one of which is substring matching. Okay? Suppose we want to edit, let's say search for, as I've said before several times, Skiena in the Bible. Okay? Suppose we did the edit distance alignment. Between here we have the Bible, which is a long thing, and here we have Skiena. Uh-oh, it's getting tired of me this time. E-N-A. What is the optimal alignment going to be? If assuming we have the regular edit distance cost of 111, what is the optimal alignment of Skiena in the Bible going to be?
The length of the Bible?
It's the length of the Bible. Is it the length of Skiena? What is the optimal alignment going to be? It's not the length of the Bible. What's it going to cost to find Skiena in the Bible? Okay, let's turn Skiena into the Bible, yeah. The longest match, but what is the longest match in the Bible going to be with Skiena? Okay, what? I claim you're going to find me there, although in bits and pieces. Why? In the beginning, God created the heavens, right? There's going to be an S there, right? Somewhere along the line, there's going to be talking about a K, and an I, and an E, and an N, and an A. Does everybody agree with that? So what is the optimal match going to look like? It's going to look like the alignment's going to be a delete, substitute, delete, substitute, right? Does everybody agree with that? That's what the alignment is. So the cost of Skiena in the Bible is going to be the length of the Bible minus 6. Okay? Does everybody agree with that? But that's not really what you're looking for, right? We're looking for the place where it looks most like the best match. Does everybody agree with that? So we're really looking for a different problem. If you want to know where is this name possibly misspelled in this other document, you want to know where is there a short place in this text where this string largely occurs. Does everybody see the difference? Okay? So in principle, they'll be talking again about some place where they talk about skin, and later on they'll talk about something else. There is probably somewhere a string of 7 or 8 characters that basically has most, by doing 4 or 5 deletions or insertions or substitutions, will find me, right? And that's what you mean by string matching. Any questions? So how do we find, basically, with more sensitivity, where is a short pattern in a big text? Yeah? You're saying slide Skiena, put Skiena here, then put Skiena there, put Skiena there. Well, maybe, but notice that putting Skiena isn't really maybe it's sort of the right idea, but it's not quite the right idea because you don't know where Skiena ends. For exact string matching, you knew where Skiena ended. If you started me in the 56th position, I was going to be in 56 plus 6 minus 1, right? Now with insertions and deletions, you don't know where I'm going to end. So it's no longer matching a whole string to a whole string. It's matching a part of a string to a part of a string. Does everybody see that? Yeah.
So you just increase the cost of deleting
You increase the cost of deleting.
in the text.
I claim that what I am going to do actually is instead mostly play with the row and column initialization. Okay? What am I going to do? I'm going to do the same basic editing function. I'm going to adjust the initialization. If I want to find Skiena in the Bible, right, or in the long text, skin on, right? Okay? I want to know what is the cost of editing this pattern all the way to the end to the text ending at some point and starting at some point. Does everybody agree with that? This is the alignment that I want. It's going to look something like that. It's going to start someplace editing the empty string into a character, perhaps, or the empty string here into the empty string. I need to make it so I am not punished for starting 3 million characters into the text. Does everybody see that? And the way to do that, I claim, is just to change the initialization condition. What I really did was change my row init. The big change here is just that I changed the row init. So the cost of editing the first I characters of the text to the empty string, instead of it being I made it 0. Can people see the 0 there? 0. This is the big difference. Okay? Any questions? Yes?
The other thing is that you want to, after you finish, you want to look at the minimum cost over all tables.
So the question is, that if I do that though, one problem is, where is my goal state? Right? I am no longer interested in the cost of editing my pattern into the whole text. I am interested in editing my whole pattern into some chunk of text, to ending somewhere in the text, right? So my claim is the other thing that is different is that my goal cell, instead of it being here, is going to be what?
Somewhere in the last row.
The minimum cost way of getting to the last row. Does everybody see that? I have to get to the last row because that means I've matched all of my pattern. And it might be here, it might be there. I've got to check all of them and find them in. Yes? You can't see, you shouldn't see it from there. Okay, go. Zoom. 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 Now let's see what this is like. Boom. So note change. Note change. Now it says, basically for every cell, the ith cell on the initial row, the cost of getting to the ith column in that first row, 0th row, is 0.